All right, so we have these three things here that we wanted to. So the current voltage relationship was what we established last time. Within the domain of Laplace transform. So we want to establish a few things. Um, for those persons who iterate, um, not taking it for granted. So I am going to current divider rule. Um, Current divider rule, we want to define the voltage across the resistor R2. Um, so we would say V out is equal to the current times R2. I would say the input, let's call it P in, is equal to I times R1 plus R2. So therefore, we would say that V out over V in would be equal to I R2 over R I R1 plus R2, which implies that you can cross all the I's. So V out is equal to R2, R1 plus R2, V in. So that is the current, the divider rule. So
Current or voltage divider rule, sir?
voltage divider rule, sorry.
Okay,
I don't know why I'm saying current.
all right.
So now, so if we have a filter, let's just make up one. And we said find the transfer function, which is the ratio of V out to V in for this filter. Then what do we do? Well, we would redraw it whether in our heads or on paper. And we put in the S values for it. So 2 Henry would be S times L. So S times L would imply that this would be, the L is 2. So therefore it would be 2S. That would be the And this is 1 over SC, the capacitor. So therefore, the capacitor is 1 farad, so that's 1 over S. And the resistor is 3 ohms, so that would be 3. So these two are in parallel. The capacitor and the inductor are in parallel. So to find the total for impedance, so the impedance in parallel would be equal to product over sum. So that would be 2S times 1 over S over 2S plus 1 over S. And so that would be 2 and S, so that's 2S squared plus 1. And we are dividing, so that would end up as 2S over 2. 2 divided by 2S squared plus 1 over S is 2 multiplied by S over 2S squared plus 1, which is equal to 2S over 2S squared plus 1. So that would be my transfer function, V out over V in. That's what it would be equal to. No, that's well, we're
Isn't
thinking
that
about
the
too much things. That's
impedance
the parallel
between?
for the parallel section.
Yes, sir.
All right, so now we want to find a transfer function. And so we're going to use a voltage divider rule. So we're going to call over here Z1 and well,
Sir, we wouldn't add the
let's
3
call
3 ohm
this is Z1.
resistor.
Yeah, so that's what we're going to do now. So
Okay.
we are saying now that V out over V in would be equal to Z2 over Z1 plus Z2. So that would be equal to 2S over 2S squared plus 1 divided by 2S over 2S squared plus 1 plus 3.
Sir, my
That's
lord.
S over. All right, so this is, yeah, follow up to here, so what we saying?
Sir, where would Z1 be?
So we're calling here Z1. And this is Z2. So Z1 is the resistance, and Z2 is the impedance of the inductor and the capacitor in parallel.
Okay.
So we're saying Z2, which is 2S over 2S squared plus 1 divided by Z1 plus Z2. So that's plus 1 divided by everything over common denominator. That's 2S squared plus 1 is 2S plus 3, 2, 6 S squared plus 1 plus 3. 3 ones 3. So that is going to be equal to 2S over 2S squared plus 1 times 2S squared plus 1 over 6S squared plus 2S plus 3. So now our transfer function,
Sir,
our V out, yes,
Z2 is the parallel impedance.
yeah.
Um,
So
so
we're
could
calling
it,
Z2.
because I have two different presentations. Right.
Question? I didn't hear it.
Oh, I was
So
saying
this
for
is Z2. What is the question?
oh, no, sir, that was the question, sir, because you had the parallel symbol and then I saw Z2, so I was wondering where Z2.
Sir,
Okay.
you said the transfer function is
Uh-huh.
the ratio of the output over the input. But it
Mhm.
seems as if we're equal to Z2 over Z1 plus Z2 as the divider, the voltage divider rule.
Mhm.
Sir, looking on the circuit, I was like wondering how Z1 end up being 2S over 2S squared plus 1 plus 3, and the output.
No, look at it.
Uh,
I was just using the associative property Z2 plus Z1 I saved because Z1 plus Z2. You know. So it's just that I put it down first. Yeah, so this is Z1 and this is Z2.
mm-hmm.
Yeah, you understand? So it's just that I put Z2 plus Z1 instead of Z1 plus Z2, but it's the same thing. All right, so
Okay.
the impedance is Z2. So this is Z2. This up here is Z2. Look here. That is Z2 that you're looking at.
Mm-hmm.
And up here is Z1.
Okay.
So Z1 plus Z2 and Z2 plus Z1 is the same thing. All right, so our final output now, V out over V in is equal to 2S over 6S squared plus 2S plus 3.
Sir, it's because me I wonder why we add back the input, the output to the input if it's V out over V in.
Add back the output to the input.
Yes, sir, because I'm assuming that Z2 is the output and you said Z1 is the input, but where you have Z1, Z2.
No. Z1 is the input covers all of the impedances, so it's everything going wrong. So it's Z1 plus Z2 covers the entire input. Z1 is not the input. It's Z2. The input covers everything that if I am over here and looking at the circuit, I am seeing everything. I'm seeing this and I'm seeing this, the 3 ohm, and I'm seeing the parallel section. If I'm over here, I'm looking at, if I'm over here, I'm looking at the circuit. The output that I'm seeing is the parallel section. But if I'm looking at the input, I'm seeing everything going around. So the input is everything that I'm seeing from looking from where I call VI. So that would be the 3 ohm plus the parallel section.
Oh, okay, sir. So the input is everything,
So
where
the
the
input is not
output,
the input is everything.
yes, and the output
Is across where you take it. Yeah.
Is opposite from the, okay, all right.
Is where I'm looking to take the voltage.
Okay, okay, sir. Mm,
All right, so this is my transfer function. Right, so we can ask ourselves some questions, but there's some other things at ground that I want to cover.
So do you define transfer function? What it means?
Huh? If
What does
I didn't hear,
transfer? I was asking what does transfer function mean? So,
what they mean? Okay, so let me write some questions. I wasn't going to do that, but let me write some questions. So write down the differential equation governing the so now we want to write down the differential equation governing the input and the output. So if I have then what I can write is if I cross multiply, then what I'm going to have is 6s squared plus 2s plus 3 v out is equal to 2s v in. Now s squared means take the second derivative, so this is going to be 6 d2 v out dt plus s means take the first derivative, so that's 2 dv out dt plus 3 v out is equal to s means take the first derivative. So this would be my relationship, differential equation relationship for the circuit. Suppose I ask myself another question. Find voltage output at t equal 3 seconds if the input is a 5 volt DC. All right, so we want to look at that. What's the output at if I'm looking at the circuit, what I want to find out now. So let me just draw it back over here. So So I apply a 5 volt input so that bit, and I want to find the voltage at 3 seconds when I put a 5 volt source over this side. So how do I go about doing that? So the whole entire thing about finding a the transfer function is that, like I said, it take the calculus and turn it into algebra, and then it's supposed to make our life easier. Can I work out this second question that I wrote down?
Hold on, there, sir. 1 minute, 1 minute.
So as I was saying, you put a 5 volt source and you want to find the voltage at T equal 3 at any time T. But we have put the specific thing. So we want to know what is the voltage for this thing at T equal 3. Then we can start working out.
Can start now, sir. Sir, can start now.
Mm-hmm.
Okay.
All right. So now, where we're starting from is we have the transfer function. So we know that V out, V in is equal to 2s over 6s squared plus 2s plus 3. So V out is equal to 2s 6s squared plus 2s plus 3 times V in. Now we are told that our input is in the time domain. Our input is 5 volts. A DC input of 5 volts. So basically we turn on the switch, 5 volts time passes. So what would we in the S domain, what would we write 5 as in the S domain?
Sir, it would be 5 over S.
5 over S. All right, because when we have a regular voltage, we get right, that's 5 over S. So now, so we replace, so now we have V out is equal to 2 over S, 6s squared plus 2s plus 3 times 5 over S. So this is going to be 10 over 6s squared plus 2s plus 3. That's what V out is equal to. Now, So we want to use the Laplace transform table. So therefore we have to get rid of the 6 in front of the s. So that we're going to divide everybody by 6. So this is going to be 10 over 6 up top. Divide 6x squared by 6. That's going to give me s squared. 2 divided by 6 is 1/3. And 3 divided by 6 is a half. No, I didn't set up this problem to work out what I'm working out now, but the question was asked. So we just have to sort it out. So to further work out this problem, we have to go complete the square. So that's 10 over 6. And to complete the square is s plus a half of a third is 1/6. Plus, and we subtract out back the half. I mean the 1/6 squared minus 1 over 6 squared. That's how I remember to complete the square. You use whatever method you use. So that's 10 over 6. S plus 1/6 squared plus a half minus 1/6. With my calculator, not stressing any brain cells in a pandemic. I get 17 over 36. So now I'm going to go to the Laplace transform table.
Sir, could you go back out so we can see it from the top? Zoom up. All right, sir, that's good.
Okay. So now, so let me find the Laplace transform table.
I think we $400 for you, Lauren. Start. It's a prosperous start and that. Yeah.
All right. Working from home, people.
Sir, scroll down a little bit, sir.
Sir, you can move ahead now.
Look, I can step away from the computer. The same soon come.
Oh.
Sorry about that domestic crisis. This is part of the dangers of working from home. So which part we do now? Oh, so we are at now V out is equal to 10 over 6 s plus a half squared plus 17 over 6. And so we go to the transform tables. So the transform tables, the one that we would use for the transform is this transform here. So let me write it down. So let's go back, we write it down. So that's e to the at sine bt is equal to b over s minus a squared plus b squared.
Sir.
Yes.
The complete square. You see, you have 17 over 36, and I get 17 over 6.
You get 17 over 6.
Yes, sir.
Maybe I was looking at my calculator wrong.
You see 17 over 30, you have 17 over 36.
Will the recording be posted same place?
Huh?
Will the recording be posted same place on YouTube?
Yeah, man.
All right, thanks.
17 over 36, you know. Try it again.
All right. So let's go back to the word. So we have a half minus 1 over 36. You get 17 over 36. A half is 18 over 36 minus 1 over 36. Yeah, those 17 over 36.
Okay, sir.
So what we have here is e to the at sine bt is b squared. That's the transform. B out T. That's 10 divided by the, I'm going to write that as 5 over E. Oh, sorry, I have to do one to fix up first. Square root. So we have to put the, so this is 10 out of 6. I'll be, so that would be the square root of 17 over 6. Take the square root of 17 over 36, that would be 17 over 6. So to compensate for putting 17, root 17 over 6 here, we'd have to put 6 over root 17 on the outside and put back our s plus 1/6 squared plus 17 over 36. Bear in mind, says you ask about it. So this is 10 out of 70, root 17. And then now we're going to write down E, A is in this case minus 1/6 sine root 17 over 6t.
Sir, that part where you had root 17 over 6. Where, where did that part come from, sir? What did you use to get that?
I'm not hearing you.
In
What you're saying?
the line above where you're writing now, I'm asking why you have 6 over root 17 multiplied by that numerator. Sir.
Why I have 6 over? Coffee. Sorry, 1 second. Coffee. Can you just go and feed for me, please? Can you just go and feed for me, please? All right. Yeah. Coffee, go and go feed, miss. Sorry. Yeah, you're asking why we're having the root 17 over 6.
Yes, sir.
I'm not normally at me out on Friday, so yeah. All right. So remember now the transform is s minus a all squared plus b squared, and then it has to have b on the top. So we have 17 over 36 as our b squared. So I have to take the square root of that. So the square root of 17 and the square root of 36 is 6. So that's what we put up top. And then we have to make adjustment for it on the outside. So that's why if I put 17 upon root 17 upon 6 at the top, then I have to put back 6 over 17 to cancel out back this root 17 over 6 that I put there. And then I have 10 over 6 that I have to multiply. So the transform says that what is in front of b in sign is b. So that is why I put the root 17 over 6 as b. Remember, so now this is b squared. So b is going to be equal to, if b squared is 17 over 36, then b is 17 over 6. And in my Laplace transform that I have here, I have to put b in front of the sign. So that's why I have the root 17 over 6. Make sense?
Yes, sir. So does the root 17 in the numerator cancel the root 17 in the denominator?
The root 17 in the numerator, does it cancel the root 17 in the denominator? I'm not sure. All right, so you have this thing here. So you mean this root 17, if it cancels this root 17 up here?
Yes, sir.
Okay. So we some refer. Remember now, we have to set up the thing to look like this Laplace transform up here. So that is why I have the s plus 16 squared plus 17 over 36. So to get the b up top, so I have to put the square root of 17 over 6, that's the square root of this. Now, this that I put, if you look back at this over here, so it had 10 over 6. So that is the 10 over 6 that I put outside, so that it is still there. So now I put a root 17 over 6 here. So root 17 over 6 I put there. It wasn't there before. If you look over here, so yes, if you look over here, you see that you're not seeing a root 17 over 6. So I inserted a root 17 over 6. So I have to get rid of that root 17 over 6. So I have 10 over 6. So what I'm saying, I multiply by 6 over root 17 so that they cancel out. Now this thing here is what I took the inverse Laplace transform for. That is why I get the e to the negative 1/6 root 17 over 6 VT. I know this is what is left. So now that is what I can say. I'm just left with 10 over 17. Any clearer, or we still
So now root 17 is supposed to
having
have
some issues? Huh?
6 over root 17.
What again?
You have 6
10 over root 17.
Yeah, because this,
Yeah, no, right back your root 10,
so
right?
this 6 cancels that 6, and this root 17 cancels that. So that would have leave. That's why I put 6 over root 17. So I cancel out and just leave me back with the 10 over 6, what I had before. But I want to be able to use this Laplace transform. So it have a b up top, which is root 17 over 6. Okay. So I have to fix up the transform. So now I can write this.
Sir.
No, I can write as this here. Yeah.
Go back again. The 10 over 17. Go back again right there, sir. Not too sure.
So it's supposed to be 10 over root 17.
Yeah, that we not say, sir. All right.
Oh. Okay.
That me not talk, sir. What are?
Oh. All right, so this is 10 over root 17. So now when we plug in 3 inside there, that's going to be 10 over root 17. A to the minus 1/6 times 3 sine root 17 over 6 times 3. And they're going to work out what that is equal to. So e to the minus 0.5. I'm putting calculator in radian mode. Root 17 divided by 6 multiplied by 3. Find the sign of that. Times 10 divided by root 17 times exponential minus 0.5, and I get 1.297 volts.
So that's it, sir.
Yeah, so the voltage at time t equal 3 is 1.297.
Okay.
Tell me when I can move on. Yeah, tell me when I can move on or no.
Can move on, sir.
All right. So now, there's one other thing that I wanted to talk about. All right. All right, so we want to All right, so we want to write down, well, we're not going to write down, we're going to derive the relationship for the two op amps, the inverting op amp and the non-inverting op amp. Let me start with the non-inverting, as I find that that is easier to deal with. Now, the non-inverting op amp is one in which we have a feedback. You have two resistors connected to the output, and you have a feedback resistance that is here. So this thing works like your toilet tank. It works as just like any control system that have feedback, whether it be in your body or it is an electrical feedback system or any other feedback system, chemical, all of them work the same way. So what is happening is that part of now, the part of the voltage is determined by these two resistors here because they form the same R1, R2 that we're talking about, voltage divider. Is the same thing that we're talking about here. All right. So how does your toilet tank work? It's the same thing as this here. So if you understand how your toilet tank works, then you understand how this works. So somebody explain to me how your toilet tank works. Yeah, man, is a question I'm asking.
Sir, you mean how it fills up and it releases whenever you flip the switch, sir?
So how it works? So you have your tank.
Energy, sir. I get back energy.
When
Sir, I mean, back off, sir.
Sir,
right, so as the water fill up, the ball rises and then it's going to lock off.
Yes, sir.
It's going to lock off the what is it?
Flow of water.
Okay, so you're going to lock off the flow of water. As the ball rises, just more and more it lock off the flow of water, so the flow of water gets less and less until it turn off when it reaches the level. No, sir?
Yes, sir.
And I'm saying that these two things. So these two things are exactly the same. They're functioning exactly the same way. So the derivation is basically the same thing. So people who study control like myself, that's exactly the same thing. We're not seeing any difference between it. So let us discuss all this thing here work. First of all, peace of mind. So this resistance, let's say this is 5 ohms and this is 5 ohms. So if I have 10 volts across this, at this point, the junction between the two resistors, what would that voltage be?
Sir, can I repeat, sir?
I'm saying that this resistance, R1 is 5 ohms, R2 is 5 ohms. And let us say that the voltage across this, the two things is 10 volts. What would the voltage at the junction? I'm going to call it A. What would be the voltage at A?
5.
5 volts. And so because it's half of the voltage. Now there's a wire connected A to the inverting terminal. And we measure voltages with respect to ground. So the voltage that we are measuring is the voltage across R2. All right. We measure voltage with respect to ground. So if it's 5 volts here, it's 5 volts with respect to 0. So therefore, the voltage at this point, this junction here, is 5 volts. All right, so bear that in mind so that for our discussion. And then we can write down what we say in English in maths and derive the relationship that we want to derive. So so let us say for argument's sake now, we put 4 volts at this juncture here. Initially, this thing would be 0, and we turn on the switch and 4 volts goes into the non-inverting terminal. So the output is an amplifier, so the output starts to rise. So now it starts to rise, and let us hypothetically think it reached 2 volts. So the voltage across the output is 2 volts. What would be the voltage across the voltage at the non-inverting terminal be?
Sir, go again, sir.
Just a volt.
I the voltage at the, I put 4 volts at the positive, the non-inverting terminal. And so initially everything is off. So I put 4 volts, and just like the tiny tank start to fill up. So it's empty and the water start to come in, the voltage start to rise. So I'm saying now, let us say that we're at 2 volts, the output reach 2 volts. What would the voltage at the non-inverting terminal be? If this is 2 volts, if the voltage across the output is 2 volts. Or you get 7.
Sir. Sir, because you say right at the junction between.
Or you get 7.
Sir, you say right at the junction there, so because at first you have 10 volt, right? Between the 2 resistors. So you share and a half, so you have 5 there, so what's the output, which is 2?
No.
That'd be 6.
Oh, hold. No, wait. We'll start over from beginning. We'll flush the toilet. And we'll start over from beginning. So not 10, not there, no.
Okay.
So we started from 0. And we say we reach up to 2. What is the volt? This is, so the across the output is now 2 volts. What would the voltage here at the non-inverting terminal be?
1, sir. 1, sir.
At the inverting terminal, sorry. 1 volt.
Yes, sir.
All right. So it's at 1 volt. So remember now, is a differential amplifier. So it's 4 minus 1. So initially it was 4 volts flush going to the amplifier and starting to think to rise. Now it's 4 minus 1 volt. But that means still we continue to rise. So when I'm at 6 volts, what would be the voltage at the inverting terminal be?
Would that be 3 now, sir?
Huh?
3.
One again?
3, sir.
3. So 4 minus 3 is 1. So therefore, things still pouring into the amplifier. So the voltage is going to continue to rise. Now, when I'm at 8 volts, what's the voltage at the inverting terminal going to be?
4.
4. And 4 minus 4 is 0. So it's going to lock off at 8 volts. And that is where it's going to stay. So the amplification factor is times 2. All right, so 4 volts in and you get 8 volts out. And it's going to reach 8 volts and stay. And if for some reason, let us say it happens to go to 9 volts, then, sorry, let me use nice whole numbers. 10 volts, then what will happen is that the terminal here it would be at 5 volts. 4 minus 5 is minus 1. So what is going to the amplifier is going to do is push it back towards the 8 volts. It's going to be negative, so it's going to cause it to go down, go back down. All right. So put the voltage here, it's going to rise, and then the ratio of the is going to rise until the two voltages are equal. And then it stops amplifying. So let's write that down in words. So the amp is stable when V plus equal V minus. That's what we're saying, when the two voltages are equal. The voltage at the plus is the input voltage. The voltage at the minus. Now, we're not using 5 and 5, we're going to use R1 and R2, but we know the divider, voltage divider rule that says that the voltage at the point A, which is the voltage at the negative terminal. The voltage at the point A and the voltage at negative terminal are the same because we have a wire connected both of them. So the voltage at minus is going to be R2 over R1 plus R2 V out. So therefore, we're going to say V in is equal to R two over R1 plus R2 V out. So we want, so we have V in over V out is equal to R2 over R1 plus R2. Our V out over V in, which spin it around, is R1 plus R2 over R2. So we arrive at the formula. 2 over R2 is 1, so V out over V in is equal to 1. R2 over R2 is 1, right in that first, plus R1 over R2, right that second. Okay, that is how we see the formula in the book. All we do is replace that impedance, we replace R1 and R2 with Z1 and Z2.
Sir, in regards to this particular circuit, sir, are the two resistors normally equal or they can be of different values? For R1
That's what I'm saying now. R1 and R2 don't have to be the same. It's never the same actually. It's very rarely that they are the same. Sorry, it can be two different. And now I'm saying to you now that it can be a capacitor, an inductor, it doesn't matter. Because if it's Z, it's the same thing. All we do is write down the value in S domain and proceed. So we can write V out over V in is equal to 1 plus Z1 over Z2, where those are impedances. So next, I want to go to the can move over to the inverter.
Yes, sir.
All right, so let me go. All right, so let me go over to this one here. The inverting amplifier, it takes a positive voltage. So let's say they are putting +5 at the input, and +5 is measured is 5 above 0 volts, and over the next side we'd have a negative inverted voltage. So whatever is positive over here is negative over here. So the first point that we want to make is the point that if you're going along a line with opposite to the maths people, then it should be the other way around. But if I'm going from here to here, then I must pass through 0. If I'm going from positive to negative, then I must pass through 0 at some point. I'm heading along this line here. You agree?
Yes, sir.
All right. So if I'm heading along this line here from +5 to -10, so I'm going along here from +5 to -10. Without much discussion, what I will say to you is that we know that the point where it is 0 is at the junction. So because I never have a name for that point. So Alex, couple times with. What is the point X called?
Virtual grounds. Virtual
Alright.
grounds, sir.
Virtual ground. I went to say virtual earth. So i.e. X is equal to 0 volts. Virtual earth or virtual ground? I remember this one. I'm always postulating, you know, so
And
this
the
generation of young people.
high impedance.
Right. Yeah, but let me say, my postulate is that this generation storing the wrong thing in them short term, in them long term memory now, and storing the wrong things in them short term memory. When you storing things like girl and boy phone number in a long term memory. Or what we did have on yesterday.
Sir.
Sir, that's not the
Answer
case when you're paying your own school fee, sir.
That's not the case.
When you're paying your own school fee.
Huh?
Well, that's not the
Oh,
case when you're
everything's
paying your
stored in a
own.
long term memory.
When you paying your own school fee,
okay,
that's not the case.
Sir, could you bring the page over a little bit to the right so I can write out what is on the non-inverter part?
Yes, I was asking if
Oh, sir, I got disconnected. Sir.
No. All right, so this point is called a virtual alert. Now, virtual alert means that it is at 0 volts. So now that has significance because the point, if I said this is the input is 5 volts, is 5 volts with respect to earth. It don't matter which earth. Virtual means not real earth, but means it's still at earth potential. So if I say the input is 5 volts, it's 5 volts with respect to earth, whichever earth I am talking about. So therefore, I know that there is voltage across R1 if is 5 volts. All right, so I know that the voltage across R1 is 5 volts. And if I know the voltage across R1, then I can calculate the current across R1. So let me write down I1 here. So I1, what would I1 be equal to? It would be equal to the input divided by R1. Now, the next thing that you're told about the operation amplifier, it has infinite input impedance, which means there's a home circuit. So you have a current and you have a junction. And this here, so if you have a current and it goes, basically it buck up an insulator. That's what infinite input impedance means. Then where is it going to go when it reaches this junction here? Not going to go this in through the amplifier. Everything is going to go up through R2. Agreed?
Yes, sir.
I don't know, pay me no mind.
Happy your mind, sir.
All right, so we're saying that not flowing into the amplifier because it block everything. So all the current that is going to go and flow through R2. So I1, so I'm going to put in a current I2 now. I1 equal I2 since op-amp has infinite input impedance. All right, so now, so all the current, so I1 equal I2. But what is I2 equal to? Well, it is 0, X is 0, and the output is V out. So we know that I2 is going to be equal to 0 minus the output voltage over R2. So what we end up having, so therefore, V in over R1 is equal to minus V out over R2. Or we can just write that V out over V in is minus, V out over V in is minus R2 over R1. And if we replace it with a capacitor or inductor, then we don't talk about resistance anymore, we just say impedances. All right, so we can go on to talk about two last things that I need to make mention of. This is just to, instead of writing down a formula, I just decided to. So I need to make mention of block diagram.
So where you have VI, is that V in or something else?
Yeah. V in. All right, if we have cascaded blocks, 2 blocks put together, then if I multiply G1 by G2, so the transfer function of is output over input. So the output over the input gives us the transfer function, which I'm calling G1. And G2, the transfer function is Y over X1, which I'm calling G2. So if I multiply G1 by G2, that's going to give me X1 over X times Y over X1. That's Y over X.
Sir, why we multiply them, sir?
Why multiply them?
Yes,
Because
sir.
when we multiply them, we get this interesting relationship that says the transfer function Y over X is equal to G1 times G2. We just multiply the two transfer functions. So we're going to use that
Excuse me,
in our
sir.
problem. But
What is x1 over x, like x1 over x and y over x1? Is that a rule or something?
So this is our input and this is our output. But it is also an input. So I'm just using a little algebra to establish a rule that if I want the input or output two cascaded blocks, then all I do is multiply the two transfer functions together. So let us talk about that a little bit then.
Sir, could this like I wasn't finished writing, sir.
Yes, sir. Just make it the last line. I can go on right same time.
Because of the questions that you're asking, I'm changing the format of what I'm doing. So So let us look at this question now. All right, we can.
Sir, bring up the page.
We can look at this question, you know.
Sir, bring up the page for a second, please.
Bring up.
Yeah.
Mean down or up?
Up, sir. More so above. Yeah. Stop. So you can bring it back to where it was.
All right. So we want to analyze the circuit and find transfer function. So we can simplify our work using what we have just said here. We can divide the circuit into G1 and G2, two separate circuits, and find a transfer function for each of them. So let me do the easier one first, G2. So we have
where's it?
capacitor.
Those are ones and like resistance and farads numbers.
Yeah. Mm-hmm. So this is 1, and this is 1 over 2s. So G2 is going to be equal to 1 over 2s over 1 plus 1 over 2s. So that's 1 over 2s over, that's 2s, and that's 2s plus 1. So G2 is equal to 1 over 2s plus 1. So like I said, we have divided our circuit into two.
Sir, one question. Does it is commutative, right? Means if we divide the circuit, like how you divide the circuit G1, G2 at that point. For example, if I had done it or I divide it right before the capacitor going into the inverting.
You mean here?
No, behind the amplifier, right at the capacitor, right in front of the capacitor.
Here?
A little bit before, not in between the capacitor and the resistor, before or after the capacitor, I should say then. Right where the grounds, virtual grounds.
You mean here?
Yes, sir. Virtual grounds would have been. Yes, sir. And I'm
the problem you have with that is that here's the problem that you have with that now. That there's no input-output relationship that you can get there. Because basically you just have it will just be a line.
Okay.
Remember say your input is here. So your input would just remember say no, you know, this would be 0. So this would just be input.
Okay then.
Right? Remember this point is a virtual arc. So you have to have an input and then you know, so here's our output. There, if it had not, where the circuit would normally exist on its own without any additions, then no, you have to look at it and
Okay, sir.
decide input, output, draw me line, input, output, draw me next line, and so forth and so on. All right, G2 now, G1 now. Is a little bit more involved because now we have a resistor, which is 1, a capacitor, which is 1 over S, into a capacitor, which is 1 over S, a resistor, which is 1. So in this case now, Z1 is equal to 1 plus 1 over S. And Z2 is 1 in parallel with 1 over S. So it is product over sum so that is going to be 1 over S into S plus 1, and then so it is 1 over S plus 1. And then G1 now is equal to negative Z2 divided by Z1. So it is equal to minus 1 over S plus 1 divided by S plus 1 over S, which is equal to negative 1 over S plus 1 times S over S plus 1. So that means that G1 is equal to negative S over S plus 1 all squared.
Sir, you can zoom out, please, so I can. Sir, if you can zoom out, sir, because the right above where G2.
Sir, in the meantime, sir, would you mind going back over what it is minus Z2 over Z1?
Remember now, this thing here is an inverting amplifier. And the transfer function for the inverting amplifier is Z2 over Z1. This part here is Z2, and this part here is Z1. So we just apply the inverting formula to it so that we can find out. Yeah, so we look at the thing, Mr. says an inverting them, and we just say Z2 divided by Z1.
Okay, sir. Thanks, sir.
So we can find the relationship between V out and V in by just saying that's equal to minus S over S plus 1 squared times. Right, everyone can move on.
You can move on, sir.
All right. All right, so now,
Sir,
the next thing says,
is G1 conductance, sir? Is G conductance?
no. Don't have anything to do with conductance. I could have used X, Y, Z, A, B, C. I just chose G because it's G them always use. If you look in the book and have a black diagram, then you're going to see G. But G don't have nothing to do with conductance. Nothing at all. Conductance, remember, is one over resistance. So we're not talking about that. All right, it's not that G.
Right.
And the reason why I use G is, as I said before, is G you see out of the book them use. All right, now it says a spike occurs at time t equal 3 seconds. So at a spike, so you have your system, your input, and what it is saying is that at t equal 3 seconds, you have a 5 volt spike. So what is the output going to look like? What is going to happen at the output? Is it going to go up? Is it going to go down? So we are going to calculate. So first thing that we have to do is, so the input is a spike at t equal 3 seconds. So we write it like this. So is the, when you call this in maths, call it the impulse function, call it again delta Dirac function at time t minus 3. So what is the Laplace transform for that? Sorry, not, it is 5 times the impulse function. So what is the Laplace transform for that?
5e to the minus 3s, sir.
5 e to the minus 3s. So our V out is equal to minus S over S plus 1 squared 2S plus 1 V in. So V out is equal to minus 5S e to the minus 3S over S plus 1 all squared 2S plus 1. So now, so we have to convert that to time domain, because S domain fine with the algebra is fine, but then we have to convert it to the time domain. So we have to do a little bit of maths. So here's how the maths part works now. We are going to ignore the e to the 3s for the time being. So we're going to do a partial fraction expansion on minus 5s So we're going to ignoring the e to the trace. All right, so it is still there, but we are going to ignore it for the first part of our calculation. And then stick it back in at the end. So we have minus 5s over s plus 1 squared 2s plus 1. And so what will be the partial fraction expansion for that, you know? Let me start it. It will be a over s plus 1 plus
over s plus 1 square, sir. Plus c.
Mm-hmm. And remember, so when we have a repeated root, we have to write it as s plus 1, and the next one is s plus 1 squared, and then the third one is c over
Plus c
2s
over
plus 1.
2s plus 1.
So if we combine that's a to s plus 1 2s plus 1 plus b into 2s plus 1 plus c into s plus 1 squared. So therefore, we can write that a s plus 1 2s plus 1 plus b into 2s plus 1 plus c to s plus 1 all squared is equal to minus 5. Yes. So I'm going to let s equal 1 minus 1. This drop out, the a part drop out, the c part drop out. We're going to equal to positive 5 over here. And then when I put minus 1, 2 times minus 1 is minus 2. So minus b equal positive 5. So b is equal to negative 5. Then I'm going to let s be equal to negative a half. First two drop out, so I'm going to get c to negative a half plus 1 squared is equal to negative 5 times negative a half. So this is half squared is a quarter c. Equal 5 over 2 implies that c is equal to 5 over 2 times 4 is 10. Check and tell me if I'm making a mistake, because I always make more than ever. My brain is all over the place. So to find a now, I am going to let s equals 0. So 0 plus 1 is 0. 2 times 0. Yep. I didn't hear you.
So I want to the plus 1 for the c. After you square the negative half and get the quarter.
After my square, what again?
You square the negative half, sir, so you get a positive quarter. and the plus one in the bracket. What to that, sir?
No, it's a half minus a half plus one give me a half, and then I square it and get a quarter.
Oh, yes, sir, yes, sir, yes, sir.
All right, so plug in 0 inside. S is 0. S is 0. 1 times 1 is 1, so that's A plus. And when I plug it 0, C is 10. Is equal to 5 times 0 is 0. So A is also going to be equal to minus 5. So therefore, so I have minus 5s over s plus 1 squared to s plus 1 is equal to A, which is minus 5 over s plus 1 plus B, which is also minus 5 over s plus 1 squared plus C, that's 10 over s plus 2s plus 1, which I'm going to write as minus 5 over s plus 1 plus minus 5 over s plus 1 squared. I'm going to divide by s plus a half. So we're going to take the inverse transform for those. All right, so tell me when we can move on to the next phase.
Yes, sir.
All right, we can move on to the next phase. I stepped away from the microphone. Get everybody go?
There, sir, you can do your thing.
Yes, sir, you can move on now.
All right, so the Laplace inverse for the function that is there, let me call it f of t. So the Laplace inverse of this function, f of t. We'll list the things that we're going to be using. All right, so we're going to be using the Laplace inverse of f of t. First thing, we're going to be using this function here because we have minus 5 over s plus 1 minus 1. S plus 1. We're going to be using this function here because we have minus 5 and we have minus 5 over s plus a half. This function here because we have minus 5 over s plus 1 squared. And then we're going to be using this function here because when we have the e to the minus cs, then we have to, what they are telling us that we have to do is replace everything by t minus whatever c is. So when we get the function, then we're going to have to replace it by t minus 3 because remember now, we had ignored the e to the minus cs initially and just found the Laplace transform of the function without the e to the minus cs. But when we are finished, we're going to use this function. So let us deal with this first of all. So in this case up here, a is equal to, for us, minus 1. So this function is going to be equal to e to the minus a, not a, e, so it's minus 5 e to the minus t. That function is equal to e to the minus t. And the one that is a half, then it's going to be equal to minus 5 e to the minus a half t. This one, for this function here now, our n would be 1 because we have a square. And our a would be minus 1. So therefore, n is 1 and a is 1. So that would give us t to the 1 e to the minus 1 t. So that is what that function would give us. So let's go back to our board and write down those. And then we have to come back here to write down the final. We have to come back here to write down the final function. All right, so we have said that the 5 over, this is going to be equal to minus 5 e to the minus t. And the next one is going to be minus 5 t e to the minus t. And the next one is going to be 5 e to the minus a half t. But we are not finished because we want the Laplace transform, not of that function. We want the Laplace transform of minus 5s e to the minus 3s over s plus 1 squared, 2s plus 1. So V out is equal to, now, the function that we have says that if I have e to the minus cs f of s, what we write down is f of t minus c u of t minus c. So what that translates to in our solving our problem is everywhere we see t, because we have e to the minus 3s multiplying everything, everywhere we see t, we're going to put t minus 3 and u of t minus 3. U of t minus 3 means that the thing starts at t minus 3. So we're going to write down v is going to be equal to minus 5 minus t minus 3 ut minus 3 minus 5 t minus 3 e to the minus t minus 3 ut minus 3 plus 5 e to the minus a half t minus 3 ut minus 3, which basically is another way of writing it is saying that t starts at 3. So the ut minus 3, I could have written out the answer this way. Minus 5 e to the minus t minus 3 minus 5 t minus 3 e to the minus t minus 3 plus 5 e to the minus a half t minus 3, t greater than or equal to 3. So I don't have to put the ut minus 3 for all of them. I can just write it like that. So I would use this when we finish with, if we have a e to the minus cs, then we just perform the shift on everything in our final answer. All right, make sense?
Not yet, sir, but we'll look over the video.
Sir, question.
Hmm?
Where you get negative 5s e to the dot over s plus 1 all square. Right above the v naught. Where you get that from?
Where this here?
No. Right
This
above
here
the v naught. No, right
this,
above the v naught.
which one?
No, right above the v naught beside the.
This here?
Yes.
That, remember, that was what we had originally. See it way up here?
Oh.
But what I was saying is that we disregard the e to the minus 3s when we are working towards our answer, and then we stick it back in at the end. All right, so we work out the Laplace transform of the function, and then because we have an e to the minus 3s, then everything now, we have, everywhere we say t, we have to put t minus 3.
Oh,
and we have to bear in mind that after we put the t minus 3, the function starts at 3. So this ut minus 3 is basically saying t greater than or equal to 3. You must start at 3. Function doesn't start before 3. Nothing happens before 3. But then that makes sense because we said that the impulse occurred at t equal 3 seconds. So the output, you just look, they say look at the output from t equal 3 seconds and beyond to get what the output is going to be. Because nothing happened before that. Impulse function occurred at time t equal 3.
Okay, so I understand now.
All right, so we stop in there for today. Mother always tell me when much has been said, little has been retained. So, and as overstaying, me welcome.
All right, sir. Blessings, sir.
So,
Mr. Fraser. Sir, I send you a message, sir.
I hear you.
No, I said I send you a message, but I don't get a response. Mr. Gill.
On the what? On the
WhatsApp, sir.
You sent it recently.